Hello. Today we're going to talk about Chapter 20, more about tests and intervals. So the first part is just writing hypotheses, like how do we write the null and the alternative? So in this example, we have in the 1930s, experiments were done to see whether humans are capable of extrasensory perception, or ESP. So in this scenario, you have 5 cards, and someone holds one card, and the other person has to guess which card they've got, essentially. So how do we determine the null hypothesis and the alternative hypothesis? Well, remember that the alternative hypothesis is what we want to prove, okay? So we're trying to prove that these, whether or not there is ESP or not, right? We're trying to prove that that's there. So the null hypothesis would be that it's not, so it's typical. Well, what would be a typical guess, right? If you were just a regular person, right, just taking a random guess at one of these 5 cards, well, guessing the right one, you'll be right 1 out of 5 times, right? Or there's a 1/5 chance of being right. So that's the null hypothesis, okay? So where P equals 0.2, all right, or 20% chance. The alternative would be, well, when it's not, if the probability is not 20%. So is it going to be a 1-tail or 2-tail? So in this case, your first instinct might be to say, well, if you have ESP, then it must be greater than 20%. You must have a much better track record of getting the right card, right? Well, of course, there's other people out there that would say, well, even if they got less than 20% right, maybe they only get 5% of the time, that would also show that ESP exists because there's interference. I know, that sounds crazy, but it's a thing. So here, the alternative, you could just put as not equal to, okay? So the alternative can be argued a bunch of different ways. You just need to explain what you're doing and, yeah, say this is it, okay? Kind of defend it. But yeah. Okay, so p-values. You want to make sure that you're using the right language when you're describing a p-value, okay? It's a conditional probability. It's the probability that your observed statistic, okay, is true given that the null hypothesis is true. Okay, so the probability of the observed statistic given the null hypothesis is true. Okay, you can write it as a formula, see how it's a given formula or conditional probability. Notice that the p-value is not the probability that the null hypothesis is true. You won't believe how many times people will say it like that, and you'll just get all those points wrong. Okay, do not word it like this. Okay, it's very important you get the language right. All right. So the last thing is, we know that a small p-value means that the result we observed is unlikely to occur. So if it's unlikely to occur, we have evidence against the null, which means we can reject the null hypothesis. If we have a large p-value, then that means it was pretty likely that that statistic happened given the null hypothesis. Okay, so we fail to reject the null if we have a high p-value. Okay. Okay, so let's make sure we can interpret the p-value correctly. So in the first example, you have a paper reported that a 7-year risk of heart attack in diabetes patients taking the drug Avandia was increased from 20% to 28%, and the p-value was 0.03. So what does that p-value represent? Okay, that p-value is the probability of seeing such a high heart attack rate among the people studied if, in fact, taking Avandia really didn't increase the risk at all. That would be your null hypothesis, okay, where Avandia didn't really increase the risk. Okay, let's do another example. So in this example, was challenging therapeutic touch, Okay, so whether or not you could tell if a hand was hovering over one hand or the other, your left hand or your right hand. So if you just had to guess which hand, well, you have a 50% chance, right? You only got two hands. So here, it's interesting that the practitioners had it less than 50%. So notice the p-value was reported as 0.79. That's a very high p-value, which kind of makes sense because we were expecting 50% and it's less than that. So what does that p-value represent? Well, it's the probability of seeing such a low rate of practitioners detecting the correct hand, because that was your statistic that you got. All right, given that therapeutic touch is the same as guessing. Okay, so given that it should be 50%. Okay, hopefully that makes sense. All right, so let's do a 1 proportion z-test. So from the question in your textbook, it asked if helmet use in Florida declined among riders under the age of 21, okay, based on the new helmet laws. So I didn't put the whole thing because I wanted to put the answer here, but the null hypothesis would be that there wouldn't be a decline, okay, that it's the same as it was before the helmet law change, which was the p-value is 0.6. The alternative hypothesis would that it be less than that, okay, because we're asking if it declined. Okay, it specifically said declined. So we check our conditions and notice that our conditions are going to be fulfilled, the independent, success and failure, the 10% condition. However, randomization isn't really applied because you're just collecting info based on those that had accidents. Okay, so we can't really turn it into a randomization thing. We just have to note that we have to take care in it. Okay, so just keep that in mind. Once we satisfy these conditions and we noted that we have to be careful in generalizing, we can go and find all our statistics. So you find your standard deviation, your z-score, you can graph it, and you'll see that the p-value is way less than 0.001. Okay, not way less, but it is less than that. So because of that very, very small p-value, all right, we want to make sure that we can write it this way. Okay, so make sure you're understanding this vocabulary here. So think about how it's worded, okay? So it's the very small p-value says that if the true rate of helmet wearing among riders under 21 were still 60%, the probability of observing a rate no higher than 50% in a sample like this, okay, that probability is less than 1 in 1,000. Okay, that's what 0.001 is, 1 in 1,000. So we reject the null hypothesis. There's strong evidence that there has been a decline in helmet use among riders under 21. You want to make sure you're able to explain the math to apply it to in context. Okay? Okay, so while the p-value is important and gives us information on the chances of getting a test statistic like we got, but it doesn't tell you how much lower, right? It doesn't tell you how much the rate has actually decreased, right? Because that was just one example. So you need to create a confidence interval, right? So that way we can determine exactly where we think the new probability lies. And that lies from 0.47 to 0.54, which is strong evidence that the rate is no longer 60%, because 60% is not included. Of course, if this went from 47% to like 59 or 58, not necessarily strong evidence, but we're 6 percentage points less, right? Well, a little more than 5, okay? So that's evidence that it's no longer 60%, okay? Now, whether a change from 60 to 50% makes an important difference is a judgment call, right? In this case, you're talking about helmets that save lives. So guess what? Florida required a motorcycle endorsement, all right, to get people to not have these crashes, right? You're trying to make this not a thing. So keep in mind that your explanation, your description of your p-value, and your confidence interval is always based on, you know, the context, the example. Because if we were talking about something else, maybe, I don't know, what's something else? If we were, I don't know, trying to see how often people go out to dinner or something like that, probability jump from 60% to 55%, maybe it's not a big deal, okay? But here, you know, you interpret it different. So it's just something you want to keep in mind. Interpretation is key, and it always depends on the context, okay? There's no clear-cut way to interpret your answer every single time. All right, so while we're looking for a small p-value, we have to decide, well, what's a significant p-value, right? We talked about it could be different for different things, right? 10% versus 2% p-value is different. So what is our cutoff to make it rare enough? Okay, so that's an alpha level or significance level. So before we look at our data, before we do anything, we have to select an alpha level. So it's telling us how rare is rare enough. Like if we were trying to assess the safety of airbags, we'd want a really low p-value. So our alpha level needs to be 0.01 or even 0.001, right? We really want to make sure airbags are are safe. And so we have a really, really small p-value or alpha level here that we're trying to reach. 0.05 is kind of like your catch-all. Okay, that's like if you're not sure, you just pick 0.05 and kind of see where it goes. Okay, 0.10 is, well, it doesn't need to be super, it's not as important, so to say, as safety of airbags. Like this one is assessing whether folks prefer pizza with or without pepperoni. That's probably a big change in guesses, right? So having a 0.10 p-value would probably be more acceptable. Okay, is that making sense? So guess or select your alpha level, what you want to get that's going to prove that your statistic is rare before you get your p-value, right? Because then you're considered cheating. Okay, so what does alpha levels do? Well, it helps with the statistical significance. Okay, so what we mean by statistically significant is that our test statistic, our p-value, was lower than our alpha level. So if we said 0.05 is what we want to see for it to be rare, and we get a p-value of 0.03, we're good because it was under 0.05. Okay. The statistical significant doesn't really carry anything. Okay. It's just saying that, all it's saying is that it fulfilled the alpha level that I wanted. Okay. So we can say that if our p-value is less than our alpha level, then we can say that our test was statistically significant because we got what we wanted. Okay, but that's it. Okay, and it depends on your alpha level on whether or not it's going to be, you can say it's statistically significant or not. All right, but the p-value is what's the important one. So you always want to make sure that you provide the p-value to your readers. Always include it because you want people to make their own decision. Okay, something that's significant. What you consider statistically significant isn't the same as someone else. Like I may want a 0.05, alpha level, but you might think, no, this needs to be more serious. I want a smaller p-value. So you look at what my p-value was, what I had gotten. Okay. So here's an example of it being statistically significant, but not really important. Okay. So it's an insurance company, and they changed the cost of the policies. Okay. While there was a statistically significant difference, it was only a difference of $10. So is that really important? Okay. You seeing it now? All right. You can say the same for the, sorry, let me get a little excited here. Okay. So if you're testing a new treatment, right, how is it curing? An improvement of 10%, maybe it's not going to be statistically significant with only a small number of patients, right, in a small number of study. So a small trial isn't going to be enough. You need more for it to be statistically significant there. Okay, hopefully I'm making sense with that. Okay, so your confidence intervals and your hypothesis tests are actually one and the same kind of. So they're built from the same calculations, and they have the same assumptions and conditions. So we can approximate hypothesis test by examining the confidence interval. So if you have a 95% confidence interval, that's a two-sided hypothesis test with an alpha level of 5%. Okay, because the alpha level is so this is two-sided. So let's see. So you want it like this, and you're going to have it something over here, because it's two-sided, and you want both of those to add up to 5%. So in this middle part would be 95%. So that's why that would work. Okay, so you'd have 2.5% on each side. Okay. All right, so it's pretty cut and dry with it being two-sided. Ooh, sorry. Here, it's a little bit different with the one-sided. So if you have an alpha level at 5% and it's one-sided, you need to do a confidence level of 90%. Because if you do 90%, okay, so if this is 90%, whereas this side was 2.5 and 2.5, this is going to be 5% and 5%. Okay, and if we're doing a one-sided, we aren't looking at this one over here or this one over here, right? You're looking at either the left side or the right side. So you need all of that 5% to be over on the left side or the right side of your tail. Okay? So you need to watch that when you do a one-sided, you need to double your alpha. Okay? All right, so let's practice some. So in an experiment to test the fairness of a roulette wheel, the z-score is 0.62. So if the z-score isn't even more than 1, right? So here, that's not a big z-score. That's not far from the average. So here, you can't reject the null hypothesis. There's no evidence. All right, number 2, we are talking about the last example from the last chapter. So a bank wants people to pay their balances, so they either send a DVD trying to set up a payment plan. Well, they got the results back. Confidence interval was 29 to 45%. So the old letter method worked 30% of the time. Well, can we reject it? Okay, well, 30% is in our interval. So no, we're not going to be able to reject it. Okay. So it's possible that sending the DVDs is no more effective. All right, it's in our confidence interval. So given that the confidence interval is found in their trial, what would you recommend that they do? Okay, well, yeah, I would scrap it because it's probably more expensive and it's not really worth it, right? We can't distinguish the success rate. Yeah, I wouldn't just go off this one trial, Okay, because if we had gotten an interval of 45%, well, that'd be better than 30%. So do another example, do another trial. Okay, a sample size, increase your sample size to try and get a smaller confidence interval and see if it's closer to the 30% or 45 or kind of how far off we're going to be. Okay? Okay, so let's do an example. So take a minute, pause this, read it, and see if you can find the confidence interval, or let's use a confidence interval to test this hypothesis. So run through it, you know, your null and alternative hypothesis, your conditions, check your conditions, run your statistics, and then make a conclusion. Okay? Take a minute, pause, read. Wonderful. All right, so answer. Ooh, press the wrong button. Okay, this one. So I started over here. You have your null hypothesis and your alternative hypothesis, right? The goal is that it needs to surpass the national average. Okay, so that's why it's greater than 0.82. You check your conditions. These are all good, so we can use our one proportion Z interval. We wrote everything down. Okay, we got N, P hat, standard error, and then you get your confidence interval. So our confidence interval, okay, is between 77 and 88%. Okay, because the hypothesis rate of 82% is within this interval, we can't reject the null hypothesis. Okay, so we can't conclude that this was an effective campaign. Okay, now the upper limit of the confidence interval shows it's possible that the campaign is quite successful, but the small sample size makes the interval too wide to be very specific. Okay, hopefully that's what you got. If not, ask me in class. Now, what if we have a small sample size and our success failure condition, we can't get that in at least 10? So what we do is we add 4 phony observations, 2 to the successes and 2 to the failures. Okay, so instead of the proportion, we use this proportion. Okay, you add 2 to the top and then 4 overall. So make sure that you notice where you're adding your numbers. Okay, we're adding, we're kind of like evening it up. So we're trying to get it away from 0. Okay, when you have your p-values that get closer and closer to 0 or 1, it's skewed data. So we're trying to kind of beef it up. All right, it's supposed to give us better performance overall. All right, and it's becoming increasingly common in modern statistics. Okay, it's becoming a lot more acceptable because sometimes you just can't get enough, and sometimes your p-value is going to be closer to 0 and 1, and that's harder to detect. Okay, so let's do an example. So in this one, they wanted to compare 2 methods to alleviate pain on the outside of the wrist. So they did their sample, but it only had with 3 failures. They don't satisfy the success failure condition. Okay, so we can't use a standard confidence interval. So we use the +4 method. Okay, so how you would do that, you add 2 to the top, 4 to the bottom, and then that changes it. Plug stuff in. Okay, so going from here, again with a with this 95% confidence interval, that's what it is, 95% confidence interval, so watch that z-score, you get this. You can write it as plus or minus, or you can write it as that interval. I think the interval is a little bit easier to read, in my opinion. You know, people have to do math here, and, you know, people aren't so good at math. That sounded rough. You know what I mean. Mental math is hard, okay? You've seen me mess up mental math, okay? Don't make me think. Just write it out. All right, so making errors. You can have the type 1 error or the type 2 error. You want to make sure that you understand the 2 different errors. Okay, type 1 is when the null is true, but we reject it. A type 2 is when the null is false, but we fail to reject it. So this little comic with the pregnancy, it's a common one to try and remember type 1 and type 2. People forget these all the time. There are, videos and tons of ways to try and remember type 1 and type 2. In this scenario, the null hypothesis would be not pregnant. Okay, so not pregnant. Okay, and so if the null hypothesis is true, okay, but we reject it. So telling a man that he's pregnant, right? That's, yeah, you know that that's true, that they're not pregnant, but now you're saying that they are. Okay, that doesn't make sense. Okay, a type 2 error is when the null hypothesis is false, therefore she's pregnant, but you say that she's not. And looking at her stomach, right? And she's even holding it like a baby. Yeah, I just thought it was funny. So what's worse, a type 1 or a type 2? So a type 1 is considered a false positive, and type 2 is called a false negative. Okay. So thinking about, your different options, type 1 would be a healthy person is diagnosed with the disease, therefore they have to go undergo further tests. Or an infected person is diagnosed as disease-free, therefore a sick patient goes untreated. Which one's worse, right? They both sound pretty traumatizing, okay, or can be. Okay, but what about the next one? Jury convicts an innocent person, jury lets a guilty person go, right? What about the next one? Passing a student who in fact learned less than 60% of the material, of the info. Guess that got cut off. Okay, so passing a student that should have failed, or failing a student who knew enough to pass. Okay, it depends in type 1 and type 2, it depends in context. Okay, just like everything else. All right, so let's see if we can identify the type 1 and type 2 error. So remember that the bank, going back to that one with the delinquent credit cards, so it was looking for evidence that DVDs produce a higher success rate than sending letters. So what would a type 1 error be? Okay, so that's remember, that's a false positive. Okay, so a type 1 error is claiming that there's a difference between DVDs versus letters when there isn't. This is going to cost the company more money and time to create and send those DVDs, and they're not going to get a real big payoff off of it. Okay, so that's a type 1 error. A type 2 error would be claiming that there is no difference between sending them, but there actually is. So the company is missing out on getting people to pay off their delinquent credit card amounts, okay, because they went ahead and scrapped the DVD idea, when actuality, it would have been helpful. Okay, so that's the difference between a type 1 and a type 2 error. Now, an alpha level, when you choose level, the alpha level, you're setting the probability of a type 1 error. Okay, so if the null hypothesis is not true, then we can't possibly make a type 1 error. You can't get a false positive from a sick person. Okay, so the null hypothesis has to be true to make a type 1 error. All right, but when it's false and we fail to reject it, we have made a type 2 error. So we assign the letter beta, so it's Greek letter for B, to the probability of this mistake. It's much harder to find the value of beta than alpha because it depends on the real parameter, and we don't really usually know that, okay? Alpha and beta are kind of like at its odds, or at odds with each other. They, if you try to eliminate a type 1 error, you're increasing your type 2 error. If you're trying to decrease a type 2 error, you're increasing the likelihood of a type 1 error. You try to lower both, okay, but that's hard, Okay, the best way to do it is to collect more evidence or collect more data. There is no other way to try and reduce both types of error, or one or the other. Hopefully that makes sense. Now, usually we don't talk about beta, we talk about the power of a test. So the power of a test, it is the probability that it correctly rejects a false null hypothesis. So correctly identifying a false null hypothesis. So when the power is high, we can be confident that we've looked hard enough at the situation. The power of a test is just 1 minus beta. Beta is, again, the probability that the test fails to reject a false null hypothesis. Okay? So the power of a test is 1 minus beta. Okay, so when a study fails to reject its null hypothesis, the test power comes into question. Okay? When we calculate the power, we imagine that the null hypothesis is false. Okay, so how the value of the power depends on how far the truth lies from the null hypothesis value. Hopefully this is all making sense. Okay. Power depends on effect, directly on effect size. So, okay, so here's a nice little example. Ooh, sorry, my font size got a little small there. Okay, so the larger the effect size, the easier it should be to see. So here you've got your alpha level and your beta level are adjusted, right? If you decrease the alpha level, the beta level is going to get larger. If you increase or decrease the beta, the alpha is getting larger. Okay. I try to visualize it like that. It makes more sense. I don't know that they're related, or how they affect each other. Okay. So if we are trying to reduce those errors, what we can do is we can increase the sample size. So notice that makes a smaller curve, and therefore our probabilities are getting smaller. Okay? So that's what I was trying to mean by type 1 and type 2 really affect each other. All right, so this is what could go wrong. Okay, so make sure you pay attention to what you're doing. It's all about the words. You know, it's statistics. It's you put all your info, you write it all down, your p-value, and really, you still might make a wrong decision, okay? But you do the best you can. You explain what you got and how it relates to in context. And, you know, if someone else doesn't agree with your interpretation, you know, then they have all the info to do that, right? To take that p-value and kind of look into it. Hopefully that makes sense. All right, what have we learned? All this good stuff. If you are lost or confused, just talk to me in class, and we'll try and do some more examples. All right.